water and the sediment that it entrains is reducing the feeding of the delta, so that gets a -2. And then, of course, down by the sea, barriers, seawalls, channelization reconfigure the deltas and can have a positive effect, so to speak, in some areas and a negative effect in others. And then the part I'm going to focus on today, anthropogenic sea level rise, the added amount of sea level rise that human beings are causing, which is gradually, we project, going to eat away at these deltas. To hone in on sort of a microscopic view of what's going on at the delta interface with the ocean, you can look at it at the salt, where the marshes are, essentially. And on the left-hand side, the far left-hand side, you can see two bars. I don't think a pointer is too useful in this context, but you notice on the fringe of each of the cartoons, there's a crosshatch bar and a solid black bar. The crosshatch bar represents the effect of accretion of material sediment from basically upstream, also local organic sediment. And the black bar represents the effect of sea level rise, so that as we move from the lower right-hand figure to the lower left-hand figure to the upper left-hand figure, you see the delta growing or expanding. That's because the accretion bar is higher than the sea level bar. But then as you move across to the right-hand column and go down, you see that the sea level bar is greater. These are conditions where the sea level bar is greater than the accretion or sediment feed, and the delta starts to shrink back. And of course, those are long-term processes. We notice in the lower two panels that storms, of course, affect this process positively and negatively by feeding or robbing the delta or feeding or eroding the delta and changing the short-term balance. So deltas are dynamic. They're always in flux under natural conditions, and humans are interfering with at least two of the very basic processes, that is accretion and sea level rise. These 40 deltas were looked at rather carefully in a study by colleagues at the University of New Hampshire, and this report is summarized in the fourth assessment report of the Intergovernmental Panel on Climate Change. I, of course, expect you to memorize all these numbers. The point of this is that these scientists projected the fate of deltas through the year 2050 with the assumption that current trends in subsidence, sediment deprivation, and sea level rise would continue. And under that circumstance, it's actually the sediment deprivation which is the major threat to the deltas. The sea level rise assumed was 2 millimeters per year, which was not a bad guess because it represents the historical sea level rise up to the end of the 20th century, but as we'll see, it's not a very good guess for the future. It's sort of at the lower limit of where things are expected to be. And adding the threat to the projected population, calculating the projected population of the deltas at 2050, and adding in all this continuing of current trends, we reach the numbers at the bottom, which are circled in red, which is that areas could be inundated, where at that time will live about 8.7 million people, and this area represents about 5% of the land area of these 40 deltas, and that's quite a discouraging picture. On the other hand, this assumes no engineering response to these threats. On the one hand, on the positive side, on the negative side, it doesn't take account at all of the likelihood that sea level is likely to rise much faster than the 2 millimeters per year, and I'll talk about that as the main thrust of my talk. But this was a very good analysis to giving us kind of the state of the art as it could be done today. So what is sea level doing and why is it rising? These are data that have been collected over the past century from flotation devices called tide gauges. That's the red dots and the error or uncertainty bars on those dots, and also the blue. But at the very end, you'll see a thin black line that's in that oval at the very far upper right-hand part of the graph, and that's recent data from satellites. And these data are all more or less consistent, and they show a consistent and accelerating trend of sea level rise, which averaged over the last century about 2 millimeters per year. But in the past 20 years, roughly the satellite era, it's averaged closer to 3 millimeters per year. It was actually a little higher in the beginning, the first few years of this century, and then shrank down a bit. So it's well established that sea level is rising, and that rise is largely attributable to the effects of global warming. In the upper panel, we see the rise in temperature over the same period, and the same graph we saw in the last slide is in the lower panel, again, showing that the two are tending to move together. So there are three processes which occur in association with global warming which cause this sea level rise. Number one, thermal expansion of seawater. Seawater takes up more volume when it's heated, like most fluids, it expands when it's heated. Number two, mountain glaciers, such as in the Alps, or small ice caps, such as that on Svalbard, far north of Norway at about 80 degrees north, melt when they become warmer. And number three, the melting adds to the mass of the ocean. And number three, there's also melting, it turns out, of the two major ice sheets that are left, Greenland and Antarctica. Both of them appear to be now in negative mass balance. That is, on balance, they're losing more by melting and by iceberging than they're gaining by snow accumulation in their centers. And that is, we think, that is the major uncertainty and the major threat for the future. The Intergovernmental Panel on Climate Change put all this information together in order to be able to project what the future of the ice sheets, what the future of sea level rise would be. And the IPCC created this table, which I failed to reference on the slide, unfortunately. And on the left-hand column, you see 6 different possibilities, scenarios for what human emissions could be of the greenhouse gases that are causing the global warming in the future through 2100. And at the far right-hand column, you see the sea level rise, which could result from each of these different emission scenarios. And there's a range for each because, again, there are large uncertainties. And the lower limit is the circle, which is in red at the top of the right-hand column, which is about 0.2 meters sea level rise over the 21st century. And the highest number presented by IPCC is at the bottom right-hand corner of the same column, and it shows about 0.6 meters. Now, this is quite a substantial amount of sea level rise. Just where I come from in the east coast of the United States, a meter of sea level rise vertically takes away, roughly using a crude rule of thumb, about 100 meters horizontally of land loss. And of course, in areas that have even flatter coastlines than the east coast of the United States, like many deltas, for instance, it can take away, the multiplication factor could be much higher. It could be lower in bluff-like areas, of course. But the IPCC also noted that it was not able to take account of a very important confounding factor, and that's what the black circle shows. Namely, it was not able to account for changes in flow of the ice sheets. Yes, the big ice sheets of Greenland and Antarctica don't sit still. They are not frozen to their bed. They do flow, and they flow towards the sea. And that flow, along with melting at the surface and at the base, are the important sources of loss of the ice, and we are unable, for reasons I'll show you in a minute, to reliably calculate what that flow is going to be in the future. There is a second confounding factor in figuring out what future sea level rise will be, which relates to the local consequences of ice sheet loss and some other local factors. It turns out that if you take a meter equivalent of sea level rise in the form of ice off Greenland, say, and you dump it in the ocean, it doesn't raise sea level uniformly worldwide, but raises it by different amounts at different locations. And that presents a much a daunting complication for calculating what sea level rise will be, say, in Bangladesh versus the delta here or anywhere else. And it's a factor which, although it was vaguely known for a century, has only been recently accounted for in calculations of the amount of sea level rise. Now, what's the threat from ice sheets? Well, it's rather large. The lower left-hand panel shows you that Greenland contains an equivalent of 7 meters of sea level rise were all the ice to wind up in the ocean through either this dynamic motion of the ice or through melting, and that Antarctica has 2 different parts. The western part contains an equivalent of somewhere between 3 and 6 meters of sea level rise, so I'm roughly saying 5. The eastern part of Antarctica contains 52 meters of sea level rise equivalent. That is believed in large measure, not entirely. There are some fringe areas where what I'm about to say is not so, but in large measure to be resistant to global warming unless we get a lot more warming than is projected to occur in this century. So I'm not going to concern myself with it for a moment, noting that 7 plus 5 equals 12 meters of sea level rise, and that's enough to have to worry about in the context of deltas. Now, as I said before, we don't understand very well why ice does what it does, and I'll show you a couple of pictures which illustrate the point. This is a part of Antarctica called the Larsen Ice